we have started the single degree freedom system for the damped vibration. So we have checked how the face portrait we can draw, and also we have checked how we can able to calculate the time period from the potential energy function. We have also studied how the energy of the system is like how we can able to calculate the energy of the system, which consists of the two terms, kinetic energy and the potential energy. So, and we have also seen that once we like the face portrait, in the face portrait, if we see that each curve in the x and v plane are actually representing a constant energy. Once we are looking that curve in the face portrait, for the undamped vibration, it shows a constant energy. And once we are talking about the damped vibration, in that case, this thing is spoiling down to a zero state. So it's constantly losing its energy. Okay. We have also seen that in case of the undamped vibration, how the energy is remain constant. We have seen it analytically, and also from the graphical manner like a face portrait we have seen that. Then we go through this full calculation for the undamped system to calculate the natural frequency of the system. We also discussed that this gives a time period, but this time period is not that much useful once we are talking about the linear vibration, because there are some simple method also to calculate that. But once we are having some type of nonlinear force function, in that case this method is one of the very fundamental of that nonlinear dynamics. Okay. Then we have started looking if the structure is subjected to some force vibration, mostly the harmonic force, then how the response of the structure we can able to expect. So there we assume the force also as a harmonic force, which is F into e to the power I omega t, and we have seen there is a two type of motion. One motion is the system's own vibration, which is the natural mode of vibration of the system, and another is the drag due to the force vibration. So we have seen both the state, but we derived only the solution for the means we have derived the complementary. So we have seen how the equation of motion looks like. We have identified that equation of motion is no longer remain homogeneous, rather it become heterogeneous. So to solve the heterogeneous differential ordinary differential equation, we have to have the complementary part of the solution and the particular part of the solution. So that complementary part of the solution actually die out with time, because it has its damping coefficient here, that is e to the power psi omega t. So this is always a decaying function. So once we can see that time is increasing, so e to the power psi omega t, it will start getting decayed. And the other portion a omega dt into b sin omega dt, means a cos omega dt plus b sin omega dt part, that part eventually die out because of presence of e to the power psi omega t as a multiplying sign. So this portion, this complementary part, is known as transient vibration. So this transient phase die out eventually, and the particular part is the steady part of the response. So that steady part of the response remains with the system until and unless the force vibration is going on. Now if you stop the force vibration, obviously the particular part will also stop, because that particular part is valid once there is a force. Okay. So up to this stage we have seen, and then we try to identify that in the particular part we have seen that the presence of the complex number, and we start discussing that what does the meaning of that complex number. So there we see the concept of, from the concept of face portrait, means from concept of the Argand plane, if we start drawing or mapping like each of the force component there, then we can perceive that that the imaginary part is nothing but the phase difference. And so we have made these diagrams where like a x-axis, this is xp, this is x dot p, and this is x double dot p. And we see that the three vectors, one is corresponding to the inertial force, another is corresponding to the damping force, and another is the restoring, elastic restoring force are there, and their combined vector we can also able to locate. And that is, so if we are calculating the modulus of that one, that can give the response in the, when the particular response we can able to get from there. So that gives the amplitude, how much it is reducing, and whatever the angle it is, it will tell that the response will be shifted by that much of phase angle. Okay, we will see more detail what does the meaning of the phase angle exactly. Maybe I can understand that that's definitely remaining a question, that okay, how the phase angle actually can be perceived. So we will come into that point. Okay, so up to this stage we have studied in the last class, and we also identified that the vector, like a resultant vector, modulus of that resultant vector is nothing but the dynamic amplification factor, because stiffness is defined as force divided by the displacement. So if we are giving, if the amount of force required for unit displacement is termed as the stiffness. Now, once we are talking about a dynamic system, in that case, what is happening? We are not only having a static stiffness, additionally, we have damping, we have inertia. So these three factors combinedly gives a stiffness. Once you are making a unit deformation, that unit deformation involves the component of that three things. And here unit deformation means unit amplitude. Don't think just a deformation, it's a sinusoidal type thing. So it's a unit amplitude deformation, it's a magnitude is unit. Okay, so in that case, how much means what is the stiffness of that complete thing? So that thing we can able to calculate from here. So that is the dynamic stiffness matrix, or the dynamic stiffness, not matrix here. Once we will see the multi-degree freedom and something there, it will become a matrix instead of a simple dynamic stiffness. It will become dynamic stiffness matrix, but that's will come in the multi-degree freedom system. But I hope you get the essence of what is the difference between stiffness and what is the dynamic stiffness. Any doubt in anyone's mind that what is dynamic stiffness? It is very clear. And that dynamic stiffness, once we are dividing with that, so we can say that stiffness equal to force divided by displacement. Now if you think that you want a unit displacement, so the force will be increased by that much of times. So that's why once we are talking in terms of the Caudal provision, we are increasing the amount of static force by the factor of dynamic amplification factor, and we recalculate the full thing. So that is the prime logic, that why in the code we are implementing the dynamic with dynamic amplification factor to encounter or to consider the dynamic effect of the forces. After this thing is clear, so that is primarily the retrospection of the last class. So now let's start from today's thing. Okay, so we came up to this stage, but we have not seen how this thing actually looks like. And also another thing is there. So now let's actually come into the things. Find that xp is this much, that is the dynamic amplification factor, and x is this with the f0. Okay, perfect. So maybe I just write it down, that how much is the x and how much is the xp. So x equal to xc plus xp. So xc is e to the power of minus xi omega t into a cos omega dt plus maybe a1 a2 sin omega dt Okay, so now if we try to first see that what is the meaning of that xp is happening here, so that is f0 by k root over of 1 minus, am I right? Okay, so now let's see how this graphs looks like. So if you see, this is the small code for that to calculate how the dynamic amplification factor looks like. So if you see, so this is written in the MATLAB live script. By the way, did you ever try it to the normal script or live script? वाह, very good. I thought maybe the answer is live ही देखा नहीं तो क्या, मतलब normally देखा नहीं, क्या live script देखूंगा. चलो ठीक है, good that you have tried. That's nice. Okay, so now let's see. If you think that, yeah, so like maybe I'll just quickly go through that. So here in the live you can see the things in the right side window. So here first I am assuming the R. R is nothing but the domain which was written as the eta. We just put it here as R. So R we are just taking some variation. Then zeta is the different damping. So if you remember the formula was 1 by root over of 1 minus eta square whole square plus 4 xi square eta square. So we are trying to see how the graphs should look like for the different value of xi, because eta is the axis. So eta will vary in the axis. So only parameter is the xi which can be varied, and you will get the different graphs for that. So you can see that first line, means the line number 3 here, is actually taking care that eta. So we are putting the variation of the eta in that line. So we can able to plot from 0.0001 with a increment of 0.00001 up to 3. So that will give the domain. So that will be my x-axis of the plot. Then you can see that we are taking the 5 different value of xi. So 0.001 means 0.1%, then 10%, 20%, 60%, and 100%. So 100% xi means it's a critically damped system, exactly. So we will have that. So we are just revolving it for the 5 times, and we try to see that how we are just calculating that. You can see that formula we have put it here, that xi equal to square root of 1 plus this plus 2g square, and then b equal to this, c equal to this, and we are just calculating first the DMF equal to 1 by a. That is your DMF. We know that is very clearly. Then I will come into what is the phase. So if you see that this portion, so this part, you can see the graph should look like this. Okay, so once the damping is like 0.001, means a very low damping, like a 0.1% damping, then you can see that dynamic amplification factor is very high, near the frequency ratio 1. Frequency ratio 1 means, what is the frequency ratio there? Frequency ratio was omega bar by omega. So omega bar is the excitation frequency, means at the frequency we are exciting the structure divided by the natural frequency of the structure. So once the excitation frequency and the natural frequency both matches very nicely, the structure will start oscillating. Think it from the real life. Like you are also some sort of like a similar guy. Once you come to that environment, you can feel a resonance. Your performance will become very, very productive. So you can also see that in the dynamics of the system also that same thing reflects. Like once the system's natural way of vibration mode and the natural frequencies matched with the excitation frequency, the structure start oscillating much vigorously, which is known as the resonance. Okay, so that shoot up is due to the resonance, and that is the resonance condition. Okay, now if you see, once we are increasing the damping slowly, then that peak is start diminishing down, but still you are getting the highest at the resonating point. That is true. Okay, so that way this thing is getting down, and you can see that the trend of the graph little bit gets changed once it is 1. Like you see that previously that peak point is start getting now shifted to the lower frequency side. Okay, it is no longer at that 1 point because it is start getting to the lower frequency side. It started coming once the damping is increasing. Okay, that type of shifts you can see. And after and at the xi equal to 1, you can see that your thing is quite, like, what to say, that your thing is like almost you do not have any peak point. It is just like a decaying type of graph. It just decays. So it is not at all like you are getting a peak in that point. So there actually the resonance effect is not there. Can you tell why this thing is happening? Can we able to somehow correlate with the mathematical expressions we obtained with this thing? Okay, maybe we will come there that point slowly. So no, so we have seen these are the observations we can able to make on that. Or if you want, I can do one small thing. I can just add one small point here, maybe, so that you will feel much better. Yeah, so you can see that I have added another line. So you see that these things are not at all having any peak. So now if you go to the overdamped system also, your peaks are completely missing, and it is also going to the low frequency side. Okay, that makes sense. So the effect of resonance is completely vanished in case of the critically damped or overdamped system. So some of the cases people try, like once people are talking about the vibration control, which is one of the most important aspect from the civil and mechanical engineering perspective, because we studied vibration primarily to control it. So in that cases, you can also see that effect of damping is very crucial, and that is one of the key aspect of controlling the vibration in the temporal domain. Okay, I mentioned the temporal domain because there is also something we can do with the spatial domain as well, but that is not the part of this course at all. Okay, so in temporal domain, damping is one of the key factor of doing the vibration control. Okay, perfect. So now if we go to the next one, so you can see that, yes. So now let me go back to the PPT and try to complete that phase 1. So these will also have e to the power of I omega bar t. Okay, because that omega bar was taken, or e to the power minus, yeah, omega bar t. Okay, perfect. So this will also have that e to the power I omega t. So that is my total response. Okay, because if you see that xp term, once we have written only this portion, that is its amplitude, but it is also oscillating. So that amplitude with that e to the power I omega t should be there. Now you should remember one point, that once we wrote that is actually not the complete portion, because this must yeah, so yeah, you can put that, or you can better use this, that the complex one, that one there, yeah, I omega bar t. Okay, so what this thing actually tells, this is the complex amplitude. So here again I would like to ask that question, what do you mean by that complex amplitude? Okay, so first let's think what is the real amplitude. So let's say if you have some graph a e to the power of I omega t, how do you perceive a? So this graph generally looks like this way. So this is my a, just assume like it just goes this person. So that is my a. Now if I say that okay, instead of this a, I am maybe having let's say c plus id into e to the power of I omega t, how that will look like? Please tell. Because if you see, actually we have that c plus I d into e to the power I omega t. How does that look like? Or if we are going to, means there is a 2 point. One is this thing and another person is this one. We can see that obviously f0 by k is there, obviously. That's okay. So now, are these two things same or are these two things different? Are you sure? Which first equation? No, forget that portion. That is the complementary part. Forget that. No, these and these. Yeah. That's not by k divided by 2. Exactly. This is scalar part, and we are multiplying it 2 times or 2. Exactly. Increase the amplitude. Perfect. But what is the amplitude? Not by k. So first one. So this is maybe 1. This is 2. So first one or second one? Which will be the amplitude? First one or second one? Or both can be okay? Both are same thing. Exactly. Could you please explain how both are the same thing? It is correct. Exactly. This is the correct answer. They both are same thing. But could you please explain how they are same thing? This we create right in the last. We normalize the complex. Normalize the complex number, but how will you realize it? That is exactly. I agree with your his point. Absolutely correct. That we normalize it, but if you try to realize that, how can we able to realize that fact? That we normalize it and all those things are agreed that point fully, but how this thing happened or how we can able to perceive it. So here, if you remember, from the very first class I have started showing a graph which is in the 3D, that the thing is getting spiraled. So here actually the point comes from where we are starting the spiral. You can think that in the last class, once we have discussed that this is my x and this is my velocity. If you remember, that graph has displacement and velocity only, nothing else. And there the graph is like going inside. And if I try to draw it like this way, x versus v into time, so you can see that the graph is going some sort of like that. If it is decaying, going like this way or whatever, this thing is happening. So the primary important point is that from where it is starting, that's the only change in these 2 points. But the radius of that circle will be the amplitude of that curve. Like if it is not decaying, let's say if it is just spiraling completely, so it will just spiral with that phase portrait complete area. And what is the amplitude? That amplitude is nothing but the radius of that circle, and the radius is nothing but the modulus of this. So this is the form of the radius. So that will tell what is my radius. Okay, and this is telling exactly at what point it is starting. because there that complex point is coming, otherwise it is not complex. And if you see the projection, because if you see the displacement versus time and velocity versus time, both are nothing but the projection of that graph into the two axes. Okay, because if you see, this is the time axis, so if you try to see the displacement versus time, so you have to just see it from that top, and if you want to see the velocity versus time, you have to see it from this side. So projection amplitude will be always this much, because you will see the circle completely, that circle's amplitude you will see. Agreed? Clear? Not clear? Okay, no issue, we can discuss on that point until or unless it gets clear. No issue. So if you see, okay, let me draw it. So if you see that we have this type of circle thing, and then they are like, it is going to that side, and we are just having like a spiraling up, this thing spiraled in the time domain, that plot. Okay, so this may be like my displacement, this may be velocity, and this is my time. Okay, so what is my displacement versus time plot? Displacement versus time plot is nothing but a sinusoidal graph. Okay, because this is nothing but the projection on that plane. Make sense? Now, what will be the amplitude of that projection? The amplitude of the projection will be nothing but the radius. The radius will be my projection's amplitude. Agreed? All of you? Perfect. So that will be my amplitude like this, and that value will be this much. It's a real number. That amplitude is not a complex number. Agreed? And once we are calculating the modulus of a complex number, that is giving that radius, that how it is revolving. Cleared? Any person, any doubt, please feel free. Because these are actually the fundamental things, like we are trying to visualizing the graph. That is the philosophy of that. So if you facing difficulty, please speak out, not a problem at all. Okay, clear up to this stage, that how this gets amplitude and all those, and where the phase is actually. Phase is that how much it was lagged. Okay, means from where it started. Suppose what is the phase means? You can think that if the system, so once we are doing that, we can also able to write this portion as like tan inverse 2 xi eta divided by 1 minus eta square. That is my phase angle. So that how much is the phase? So phase we can easily able to see that how much is in the x and y, where is the point line. So we can think that once we are exciting the system, it should vibrate along with the system, along with the excitation. Like suppose you are sitting on some type of a vibrating bench or something. So as long as the system is vibrating, you should also vibrate in the similar manner. But there is something there, and therefore that vibration get lagged. Maybe like the object is vibrating after some time. So what will happen? This portion, so like let's say this is my object and this is my portion which is vibrating. So this is moving, then it should also move along with it. Okay, then what will happen? If this is my excitation one, and let's say this is in the blue color, if this is the blue color, so both of them should move together. Maybe that is in the less amplitude or whatever the amplitude, they should move together. They must have the same phase. If it is going right side, top is also going right side, same manner. But let's say due to something, I will come like for what thing, but first assume something, it get delayed and is not going as per. Then what will happen? Maybe it will start from somewhere here, like, and slowly it is coming. Maybe like it is reaching here, that top point. Sorry. Yeah, maybe I should start like this way and go like that. So what happens? There is a lag. Once it reach its position, five furthest position, then it is still not reaching. It reach after certain time. For example, I can give another real life example. What is the phase like? Suppose we are studying the course. I am teaching that, and you are also studying that course simultaneously after going home. They are more or less in the same phase. But suppose you keep that thing after 1 week you are studying, so there is a phase lag of 1 week. So you can very easily identify that point is this way that what is the phase lag. Okay, and you can easily understood that if that thing goes long, it will get completely detuned and all those things can happen. So that same thing is also applicable for the structures as well. The structure is not very far from our real life. Okay, so I think you get an idea that what is the phase difference. Like one is the excitation and another is how the object is reacting on that. Okay, now this phase angle. So now if you see that what is that angle denoting, this is the angle, the tan inverse. So you can try to calculate that angle only. You will get how much is that. So that angle you can get tan inverse of this much, 2 xi eta divided by 1 minus xi square. Now you see what is the prime factor for which the phase changes. The prime factor is xi, damping. Damping means like something like we are getting करते हैं. That type of thing is actually the damping, that which is actually dissipates our energy and not letting us doing the work. Okay, so here also see that is the prime factor, because xi is the excitation frequency. So you are exciting something and it is reacting. That's fine. But the prime culprit is the xi. If xi is become zero, you see that tan inverse of zero, it will become zero. So it will oscillate in the same time. Okay, so if there is no damping, you will go and study the subject. Otherwise, you will start delaying and there is a phase angle start getting up. Okay, and maybe the no resonance will come. The subject will also will not get resonant accordingly. Okay, so that's how you can think that full thing. Yeah. So by the way, any question up to the phase angle? What is phase and how the phase is actually coming into picture? If you have any doubt, please feel free.
It's only due to damping, or is there any other factor?
Here, like for the single degree, it's mostly due to damping. Yeah, because you can see here that's and also that eta also plays a role, because once there is a change of the excitation frequency, that will definitely will affect. For example, if you see eta equal to 0, means it's a static type thing. There will be also no phase difference, because then eta becomes 0 and the bottom portion is 1, so it will also remain in the same phase. And you can also find some particular angle of phi, there also it becomes. And some of the cases we can see after crossing that, phase angle will become changed fully. So that also we can able to notice. Okay, any question up to this? Any question? Perfect, very good. So I can assume that this portion is clear up to this stage. Okay, so we can see that our equation can be something like this. Okay, so once we are start writing that solution, how we should start perceiving it, then we can see that. So we may sometime have some initial condition or may not have initial. So suppose if we have initial condition, then the effect of initial condition will die out here. This I omega t will be actually doing that. And it is not always the case that it will going to die out. Sometimes it may get amplified as well. For example, suppose your initial displacement was very less, okay, but excitation force amplitude is quite high. Then what will happen? You can think that the structure will have some portion where you will have this effect. After that, its amplitude will be this much. Whatever the amplitude is coming here, that will be the amplitude of the oscillation. So eventually the structure will reach that amplitude. Whatever you are starting, hardly matter, it will reach that amplitude. And it will keep oscillating from that like this way. Okay. Now, whether it will reach it from this point, this point, this point, this point, that will depend on the phase angle. That once it is reaching that position, how much is the phase angle? On that, this will depend. But it will have that amplitude similar. When suppose if it is start from here also, it can also still reach. It can go like this and then come. The phase angle will be changed, nothing else. Okay. And suppose you have a amplitude that previous A1 and A2 is giving somewhat amplitude like this. Then you can see the envelope will go like this way. So your oscillation will be like this, and then go like that. So your transient part were actually increasing, and then it finally reached to the steady part. Okay. Like for example, you were studying at some place where your width was okay, that you were doing it by yourself. Then you went to some very great college and it started resonating too much in that force. So your amplitude get higher. That thing like a very positively that amplitude is growing. And that reverse can also be possible. Like suppose it was started from somewhere here like this thing, and then that forced amplitude is somewhere coming here, so it will decay like that, and it will go like this, maybe some cycles, and then it will keep going. Okay, so whatever the transient effects are there will be changed. Additionally, not only the amplitude, natural frequency, that also start changing, because here if you see in this portion, what is the excitation, what is the frequency of the response? Omega bar, exactly. So in the steady part, so if I just say this is steady, which is nothing but this portion, steady part, your frequency is omega bar. Whereas if you see this portion which is transient, their frequency is omega d. Not exactly omega d, it is actually transiting from omega d to omega bar. It is actually transiting from omega d to omega bar. That's why it's a transient. Okay, so there the frequency is changing as well as its amplitude is getting changing. So some sort of like way the system is tuning or adapting itself with the environment. Like whatever the excitation is coming, system is try to adapting that thing. Same thing for the human life. I also don't need to give example all the time, but yeah, you can also correlate that way. Okay. So this way the things can be thought of. Okay.
Transient portion, steady state is also there. That should always be more than.
Yeah, but it will take some time to reach. that amplitude, once it try to reach, it will take some time. It will not reach at the first time. It will not reach. It will like take few cycles, because steady part, like see the way we solve the full thing. We solve the full thing in the steady. That portion we assume that it is keep going. We have no initial conditions effect. Okay, so that eventually reach, but it will take some time once the effect of your transient part or the initial part is completely die out. Okay,
So we are multiplying same time both.
exactly, we are multiplying, but there is an addition also, na? And what happened, these portions effect, that effect will be also there. So the graph cannot jump like this way, na? It will increase in a slow manner. We will plot the graph. You can see that you can see that the how the graphs are actually going. It's a smooth transition will happen. It's a transient, but still it will give a quite nice smooth graph of the transiting the thing. It will not like very abrupt things will happen. Okay, yeah, if the damping is low, sometime it may do that, but if with the damping, it's smoothly transiting. We'll see that graphs, don't worry. So we can see that this is the code for the damped vibration. So here, if you see, just okay. Okay, so here you see that A1, A2 was giving some sort of value 1 and 1. So you see it starts somewhat, some value it starts above 1. That is the initial condition effect. A1, A2 is the effect of the initial condition. Okay. Then it has a forcing amplitude 10, K is this, M is 10, and NF natural frequency it is calculating. So let's just cross check quickly how much is the natural frequency. So natural frequency is 10. Okay, fine. So natural frequency is 10 and forcing frequency is 5. That means the structure is where? Before the resonance, almost like half it was. Okay, good. So maybe we can try like 2-3 things. First, like maybe we can change the forcing frequency from maybe very less, maybe 1. So it is like a very early stage. So you can see here, primarily the graph looks like, wait a minute, maybe I will just increase the time also. 100. So you see, it's nothing but like a almost like a pre-vibration type thing, that it get decayed, and you have a very less amplification, because your excitation frequency is very low. You are almost like the very like a starting phase of the dynamic amplification factor cards. Okay, agreed? Now what I'm doing now, let me change the forcing, increasing the forcing frequency. So instead of 1, so 1, if you see, it's just almost like decaying. So maybe from 1 I will maybe going to 5. There is also similar things happening. Actually, the amplitude of force is also less. That's the point. Steam can make. Yes, that you can see. That's the resonance. So in the resonance, you see that which was like a very small amount and going out, that gets jumped up. And you see, most interestingly, where the amplitude is constant after certain cycles. That is the point, that you have some portion before we reach to a constant amplitude, and that part is the transient. So you see here, like almost like it is very evident to everyone that you see that this portion it get reduced and then it start increasing and then it become constant. Actually here what happened, the amount of initial condition is much more compared to the displacement, means compared to the like the f0 by k, because if you see what is the f0 by k, if I just quickly calculate f0 by k, that is f0 by k. So what should we do? We should make it also less, because then I can only compare, na, otherwise it's too outside. Okay, now they are comparable figures. Now you see, now you may see like very abruptly it reached to the steady state.
Decrease with 14.
No, it should not decrease the omega. Omega should be remain same. Yeah, because because you are more or less now, your initial condition was more or less in that same amplitude level. Therefore, it reached there very fast. Otherwise, it took time to reach there. First, it get decayed from like 1, it comes somewhat like range of point, means from 1 it comes somewhat range of 0.01, then it increase to some level and it gets the resonance. So that effect will happen, it will slowly transit, but here you started almost in the same level, it reached very fast. Got the point? Now you can also cross check that thing, same thing, you just make it 0.1 and 0.1, again you will more or less see the similar type of graph before, because it's like a 10 times more, you see, because that is going somewhat in the 0.5 range. Now it's from 0.1, it's got to 0.5 range, but in all the cases you will reach up to 0.5 range, because your steady vibration amplitude is more or less 0.5. Okay, so you can see here, so maybe if I just make it 0.01 also, it will again reach to 0.5 range. Look, it goes to 0.5 range, but 0.01 to 0.5 it just reached. And then if I just make it 1 as like the previous, so again you see that your steady remain 0.5, but it's come from 1 to 0.5. So this condition is not exactly, we cannot say that how long will it take, it depends from where we have started. Okay, and this thing depends on the two things, one, the what is the initial condition and how much is the damping. So if you change the damping also, it will take more time or less time, because ultimately the decaying factor is e to the power I omega t, that's the decaying thing. So that also one of the very crucial point. Okay, and once the A value is more, generally what happen, that A into cos omega dt plus A2 sin omega dt, that factor will also remain more, so it will take more time to get dissipated. Once the A value is less, it quickly vanishes. Okay, so that way we need to understand the full point, the steady and transient part. Getting clear? Anybody, any question, any confusion, anything, please?
How can color differences?
Color difference? There is no color difference, same color.
From that,
No, it's just blue only, nothing else, nothing, no other color, because we have not plot anything else, only just we plot the thing. So only single color we plotted. Means we cannot directly say also this part is transient, this part is steady. More or less, once it be like e to the power I omega t more or less become 0, that we can say it's now it become steady. Means there is some point like practically 0. It's not exactly 0, but it's practically 0. So that practically 0 point we need to find it out. Okay, and but you can see more or less, like if I say that okay, more or less in this point it become steady. Well, okay, it's agreeable that point. Obviously, I should not say that here it becomes steady in this point. That's not a correct. So you have to apply that judgment that okay, what is happening there. Okay, is there any doubt up to this stage? Any doubt? Okay, very good. If no doubt, fantastic. So now, so that is very good. Then, so this is that 3D plot. If you want to see it much better, I can also show it better. I will just reduce the time steps. Really very smooth graph. Will take a little bit more time. Look, now the curve is very smooth. You see that how the spiraling thing is happening. See? Nice. So here, now think it in the other way. That suppose now if you try to plot it in the face portrait, how it should look like. Face portrait means you are not looking that 3D. You don't have the time axis. Now you are looking just from that time axis. So you have displacement and velocity axis. So it will just have like a circular curve, but how it should look like.
Boil down to some value and
Think a little bit more, not even constant.
increase a bit, then it is the equal way.
It will become a circle or like a ellipse. So like starting from a ellipse or circle, it will coil down or coiled up and reach to another circle or ellipse, which is representing the steady state. Because steady state will be a circle or ellipse, and transient is also a circular, that's a spiral. So it will spiral up and sometimes spiraling up and down. Both those things happen, like it's coiling up and then little bit up and go, like what is happened here exactly. So that thing will be represented like this way, and then it get constant. It's just circling in that. Or it may also directly like starting and then going up and go, or it may go down and then go. All those things can be possible. I hope you got that point clear. All of you are getting? Any doubt in any place? Please feel free. If you have anywhere anything, please feel free to stop me and ask. Not a problem. Okay, here I just like forget that time to show that once we have done this, that the phase, that okay, where is the phase? So phase is also coming here. So like once we calculated that phase, that is the tan inverse of this, so you can see that how the phase is also changing. So once you have almost no damping, then you can see the structure is almost oscillating in the same way with your excitation. They are more or less in the same phase. But once it cross the natural frequency, means once the excitation frequency is just cross 1, means just cross the excitation frequency just more than the natural frequency of the system, then the response is out of phase. That is very interesting phenomena. So therefore you can see that this phase goes to pi 180, that is actually 180 degree comes, so it will go to the expression. Now once you are increasing the damping, you can see that these graphs are looking changing like this one. Okay, so you can get the values. So here the transition with the higher damping is more uniform, but your phase is kept changing. So once you are exciting the structure, they are not exactly oscillating with the same phase, rather they are slowed down slowly. Okay, once the damping is more, they are like slowly, like you can see that with the higher damping, it's just go like that. Okay, why this thing is happening? Can we physically correlate? Just any thought? What is damper do actually? Hmm? It delays the response exactly. So you can understand, and that actually gives the velocity response mostly. Because damping is more like a viscous damper is mostly worked on the velocity. So once you are having a displacement, that may like with the working with the stiffness, but once we are talking about the damping, that works with the velocity, so it will start dissipating the energy, and therefore the alteration of the phase will also get delayed. So like it's the conversion will take time. So that's why the phase get quickly change with the with the higher damping. Okay, so that two thing we have also seen in the forced vibration. Any question up to this? So up to what we completed? Forced vibration, we have seen that. Phase portrait we have seen. We have identified that how to plot that two graphs. With a force, once the force is the harmonic force. Okay. Now let's do, if we are applying some force and some constant force, if we are applying. Okay. So like you have a system, you are applying a constant force F on that. How do you feel that your response would be? We reach to certain displacement value and stay there. Okay. So for example, you want to mean like this, that it will go to certain displacement value, it will stay there. And then this will constant. This will happen. Okay. Think it. What is the meaning of a this thing? So suppose for example we have a system, very nice. We apply some force on that and we keep applying the force. Not increasing. Keep applying the force. Like for example in the gravitational field thing. Gravitational force is there. So like you have the system, you just let it go. So it will start oscillating in the gravitational force. So how do you feel that? How much changes or what are the changes you can going to see? Yeah, with the damping it will die down. So suppose if there is no damping, how it will happen? Force is constant with time, exactly. So first thing, okay, so let's try to see how the equation we can able to write, and then we can able to try to understand that how the things will happening. Okay, so let's see. So how are the forces? Mx double dot plus Cx dot plus Kx, that will be equal to F. Agreed? Agreed? Unlike to the previous case, we cannot write here F equal to F into e to the power I omega t. We cannot write that because force is a constant force. Agreed? We cannot write. How to do that in that case? Okay, first of all, what type of equation is it? Non-homogeneous. Okay, perfect. So it's again a non-homogeneous equation. Okay. So once it is a non-homogeneous equation, how can we solve that? Because you can understand this is primarily dependent on the differential equation. Like a full course, the skeleton of the course is the differential equation. So if you know how to solve differential equation, 80% of the thing is done. Other is maybe 20%. So that's okay. So that's very important thing actually. So learn how to solve the differential equation. Most all of you know that, but it's like a refreshing your idea. Okay. So here, if we see, then if it is a non-homogeneous solution, then the strategy will be how? X will be equal to xc plus xp. Same manner. Xc is very simple. E to the power of minus I omega t into a cos omega dt plus v sin omega dt. What will be xp in this case? Okay, so let's just think that suppose if there is no c dot, so mx double dot plus, okay, so yeah, if c dot is also there, so xp, if we think, if we have f0 e to the power I omega t, I omega bar t, then how it should be written? So if f is equal to f0 e to the power I omega bar t, then how will be your xp? f0 by k root over of 1 minus xi square whole square plus 2 zeta whole square. Yeah, that would be your solve formation. It is equal to omega bar by omega. Now, can I say that, and now in this case you have f equal to f0. Now, if I just say that this is equal to f0 into e to the power of I0t, can I say that? If you see, it's also correct. It's not wrong, because e to the power I0t, that is nothing but 1. So I can write it. So if I just put it here, 0 by omega, so it will become 0. So what will be my xp? Not by k. So maybe just I will do it little bit more. Sorry, this is eta, not j. So 1 minus 0 whole square plus 2 into 0 into xi. So everything will be 0 by k. So what will be my solution? X equal to xc plus xp. Solution will be e to the power of minus I omega t a cos omega dt plus b sin omega dt plus f0 by k. Okay, how it should look like? Exactly. So you are very correct, very correct, but not exactly correct. So this response, so how we can easily draw it? We know this response. Okay. You can just shift it. Done. Not a big deal. So what you said, it's very correct that it goes like, and then it will come. Just it should have a oscillatory part. It will do with oscillation. It will not just go and stay. That thing would happen if you do not consider the effect of inertia. But once you are considering the effect of inertia, this thing will be oscillating. Now, can you please tell, if you remove the damping, what will happen? removing the damping.
Continue.
Oscillation will be done, sir. Exactly. It will be shifted and just it will keep doing. Done. It will not going to decay. Make sense? How the phase portrait should look like. Yeah, think obviously phase portrait is always circle, no doubt on that. A circle or maybe some sort of like a closed loop shape. That's absolutely fine. But how it should look like? Yes, please. Please. Yes, exactly. It will be shifted. Simple. So suppose if this is the case, it will be shifted here or maybe somewhere here. And it will go. Means where it will be shifted, that will depend on the this thing. First of all, am I right? It can be shifted in any direction or it should be shifted in particular way. Suppose think this is my displacement x and this is the velocity. Exactly. It can shift only displacement. For damped also it can shift only displacement. Because velocity will have no component. Because once you solve it, it will not have anything velocity. Just if you do like a dot, it will be 0. If 0 is a constant, k is constant, so it will become has no component on that. So these two is not correct. It will be just shifted here. Okay. It will be shifted only in the displacement axis. Is it clear to all of you? Clear? And if it is damped, what will happen? Instead of a circle, it will be spiral. And the point it will be vanishing is the distance f0 by k. Makes sense? Clear? Good. Okay, it's almost 9:20. Okay, so maybe we can also like stop the class here and we may start from these in the next class. Okay.